Section 10.1, we introduced three-dimensional coordinate systems. Now, what we used to refer to as the real numbers, given as R, or block R script, we're now going to double that or triple that in terms of intersecting lines that are perpendicular to each other. So to make the plane R2, we just took one real number line, the y-axis, intersected it with another real number line, the x-axis. And that's how we describe any 2 points in a plane. I will extend this notion to three-dimensional coordinate systems, and that's how we'll get R3. R3 will come about just by intersecting those two lines perpendicularly. So that's about maxes out our drawing. We can't draw R4 in any useful way on a page here, and it's even hard to represent it in three-dimensional space too, because it is in fact a four-dimensional space. So R3 will be where we do most of our work. R2 will do quite a bit, still in the plane. We'll notice that R3 is broken up into 8 octants, just like there were quadrants for the plane. We'll have octants. If I move this drawing of the three-dimensional plane down here, we can label where you see an X, that's the positive X direction, positive Y direction, positive Z direction. These things are arbitrary, but we will always denote the first octant as this cubical space here where X, Y, and Z are all positive. So that's our first octant, just like X and Y are positive in the first quadrant. So that's the introduction to the coordinate system. The textbook's got some nice pictures and further descriptions involving that. So let's get into what kinds of things we might graph in these coordinate systems. So typically we call it any graph in the plane. In R2 we called it a curve. Now in R3 we're going to call a graph of an equation a surface. So let's see our first surface that arises. So this example asks us to describe and sketch the surface represented by x plus y equals 3. Well, let's give ourselves a nice coordinate axis to start with. Down here, we'll come back and describe it in just a moment. I don't think any one of us is going to be surprised to recognize x plus y equals 3 is a line in R2. Okay, so it's going to look something like that same line in R3, only we're going to have to address one issue. What is Z doing in all of that business? So label our coordinate axes. Again, these are arbitrary. Typically we'll draw X pointing as if it's coming out of the screen or out of the page. Y is side to side, and Z is up and down, representing our three-dimensional space, R3. So we know that in R2, this is a line. So this is a line in R2. And let's just ignore the z-axis for now. Let's go ahead and graph what this line will look like. It's got an x-intercept of positive 3. It's got a y-intercept of positive 3 as well. A little bit of algebra could remind us of that. So here we are for 2 points that are on this line. That makes drawing it rather convenient. And we'll send a line through both of these 2 points. Possibly. And so now we've got a line represented in blue through both of these 2 points. Now the only issue is there are a lot of points in this three-dimensional space that satisfy this line, x plus y equals 3. One of those is the set of points that is sitting in this xy plane that we've drawn the line in. But what we'll see is that there's no constraint on z. Z doesn't show up anywhere in this equation. So it means that z can take on any value. Well, if that's the case, it means this line can sit at every height, every level above and below it. Well, if we were to continuously run that line up and down or sort of project it along all those z values, well, what we'll end up with is a plane. And that's exactly what this thing is in R3. So this is a plane in R3. Okay, so let me drop that drawing in. And it's kind of hard to do a great drawing of this, but we'll understand that this is a plane that contains that line x plus y equals 3. And what we'll realize is that if we take any two-dimensional curve and we just plop it in a three-dimensional space, well, we get a surface. We get a much bigger thing than just a curve. All right, so let's see some more examples of this. Describe and sketch the surfaces represented by the given systems of equations. So we'll start with part A. X squared plus y squared equals 4 and z equals 2. Well, we recognize x squared plus y squared equals 4 is a circle with radius 2. That's in the xy plane. We can just draw that right away. Or we could just draw that right away. Only we have a constraint for z. Z is equal to 2. So let's keep this in mind. Now, our points x, y, and z have to satisfy this situation. Well, the points that satisfy this are a circle with radius 2, centers at the origin. Well, the points that satisfy this, well, they just have a z value of 2. Okay, so essentially what that means is we have a circle that sits parallel to the xy plane at a height of 2 on the z-axis. And I'll label these hashes out, even though it's not terribly necessary. And yeah, this circle looks something like this, more or less. It's just the circle, this curve right here in blue, and it is hovering at z equals 2, the level of z equals 2, and that's it. So we didn't get a surface in this case. The reason we didn't get a surface is because we made a constraint for z. We said z has to be this value. So let's see what happens when we don't constrain z, something similar to what we saw before. Now, moving down to the next example, we've got x squared plus y squared equals 4. That's just the circle. So let me sketch that circle for us. Let's just out. Each hash is a unit of 1, just to recognize that as we go. And I'll just draw this circle as it might live in the plane there. The problem is z is unconstrained, so it's any point that's on this circle with any z value, which means essentially extend this circle up indefinitely and downward indefinitely. And what we have is this sort of infinite cylinder that's projecting up and down along the z-axis in the xyz coordinate system, or R3. Okay, so that one forms a cylinder because z is unconstrained. It doesn't have to be a specific value. Now what z equals 2? We're just going to take this thing apart in different ways. Z equals 2, we have 1, 2, and that's z equals 2. Well, these are all the points that satisfy z equals 2. Well, they can take on any x value, any y value, because there's no prescribed rule for x or y to follow here. That being the case, well, let's put a point that'll be on this plane, and I'll just draw this plane that's sort of hovering over the xyz axis. That doesn't look very good, but what this is a plane that is parallel to the xy plane, but sitting at z equals 2. I'll work on my drawings. So that's a few surfaces, a few graphs, a few curves of sets of equations in R3. The more constraints you have, the tighter or smaller the object is geometrically. The fewer constraints you have, the more points are included, and they become surfaces and sort of bigger objects geometrically. So the distance formula. The distance formula in R3 is very similar to R2. We just have an addition of z. So we do the same differences between coordinates of the point, only we have a third component to add in there, and that'll be it. So let's have a look at the distance formula in this situation. So we want to find the distance between this point and this point. It doesn't matter which order in any of these because we're taking the difference of two things, we're squaring a difference, so ultimately we don't have to be too careful. But I'll do this. I'll keep everything in order just for neatness sake. 2 minus 7 squared plus 5 minus 1 squared. You see that I'm doing the first point minus the second point, coordinate by coordinate. negative 6 minus 1 squared, the same distance formula we've been using since middle school. And what have we got? 2 minus 7 is negative 5. We'll square that. Plus 4 squared plus negative 7 squared. This is square root 25 plus 16 plus 49. And putting that together, we got 41 plus 49 is the square root of 90. And that's 9 root 9 times root 10, which is 3 root 10. If we want to simplify the radical, it's not necessary, but why not? So 3 root 10, again, distance formula is the same thing as it was in R2, only now we've just tacked on a third component. Were we to deal with distances in 4 dimensions, well, what would happen? We'd probably have just one more letter. Over here we'd have W2 minus W1 squared. 4 dimensions is not so practical for engineers, so we'll just avoid that. Now let's see. Spheres. Spheres are very similar. Since they're so closely related to the distance formula, we'll see something similar to what we just had. Here is a sphere in 2 dimensions, as usual. To make it a 3-dimensional sphere, there's our third component, our third variable z. H, K, and L will be numbers in applied problems. That'll be the center. R is the radius. Take the square root of r squared to get r, and you know the radius of that sphere as well as its center. Okay, so in order to find the center and then the radius of a sphere, we're going to have to put it into a standard form. This problem is asking us to do that for this equation here. Now, let's group the like terms. This will be familiar once we get going with it. So we'll have x squared plus 8x plus y squared minus 6y plus z squared plus 2z. And I'm going to move 17 over to the right-hand side as negative 17. It's not crucial, but I think it's a little bit easier to do it that way. Now, we don't have the form here that we need according to standard form. So, what we need to do is complete the square. I think we all remember that. How do we complete the square? Well, just a quick refresher. We find this term, we find this term, we find this term. For each of those, we'll take half of that value and then square that half. So let's do that for the first one. So we'll say x squared plus 8x, half of 8 is 4, square 4 we get 16. We'll deal with the other terms later, but let's just write them down for now. 16 plus y squared minus 6y, half of negative 6 is negative 3, square that, we get 9. Z squared plus 2z, half of 2 is 1, square that, we get 1, so we'll add 1, and now we'll tally up all the extra terms that we added. We added this, this, and this. Negative 17 plus 16 plus 9 plus 1. It's going to leave us a positive 9 on the right-hand side. Now we can factor all 3 of these. If we kept track of that middle term that we took half of, this was 4. This was negative 3. Then we'll remember how to factor these pretty quickly and easily. Otherwise, it's still not very difficult. We've got x plus 4 squared plus y minus 3 squared plus z plus 1 squared. On the right-hand side, we have a positive 9. Now we know that our center is gleaned from this equation right here. We'll have negative 4, positive 3, negative 1. Our radius, well, r squared equals 9, so r is 3. Radius will always be positive. We don't need to worry about a negative radius or any idea of that. And there we go, center and radius after putting this equation into standard form by completing the square. And that should be a pretty standard operation. So that concludes 10.1. I'll see you in 10.2. I'll also post an extra video for the infamous problem number 7, 2 intersected spheres. So good luck. Talk to you later.